Hey guys, my name is Abdullah Joseph. I work as a mobile security team lead at a company called Adjust in Germany. And today I would like to talk to you about a framework that I've developed regarding handling obfuscated malware and in a specific way. And the technique is basically regarding handling layered Java obfuscation. Before that, I would like to talk to you a little bit about obfuscation in general. And the title of my topic, which I think I won as the longest title in tech, Semi-Interactive Simplification of Hardened Android Malware. So, as I said, I work as a mobile security team lead at Adjust. The company that I work with, it's a mobile attribution company. And we do handle a lot of we see a lot of fraudulent techniques, especially in the ad fraud industry, advertisement fraud. And my job is to basically research those fraudulent techniques and try to develop countermeasures for them. For that research, we actually do look at a lot of malware, especially adwares in the mobile sphere, Android and iOS. And with those techniques that come with that malware, you usually see a lot of obfuscation. Now, that's not something that you're going to see every time, but most of the times you do see some sort of usage of obfuscated techniques, and they are usually pretty well categorized in the industry. And today I would like to talk to you a little bit about it. So here's the agenda for today, and I think we can finish up in the next 30 minutes. So let's get started. Now, the technique that I'm going to talk about, I did mention it's called obfuscation. A lot of people call it by different names. I'm going to start talking about it in here as software protection, but you might already know about it as techniques relating to binary hardening, or US military likes to call it anti-tamper technology. And this is how I'm imagining the life of a malware author to be. I do actually know a couple of malware authors. I don't know how their 40-hour week looks like, but this is just my imagination. So you're a malware author, okay? So your boss comes in and he tells you that you need to make something that works, as in you need to make something that in the adware industry, for example, you do need to make something that can harvest as much installs as you can from unsuspecting devices by using unauthorized installs, for example. If you are working in a click farm, you do need to make generate as many clicks as you want from sources that are not incentivized users. So you do try to do things that are a little bit beyond what the regular user is trying to expect. And to do that, you do need to make it undetectable. Now, why do you need to make it undetectable? Because malware is detected all the time. It's pretty easy for TechCrunch to gain a lot of clicks for an article by just saying something like, oh, we found an adware that affected 200 apps on Google Play. And it's a big deal. And Checkpoint Research loves to also do a lot of cool sounding names for those malwares. So you got Simbad that hit in 2019 in March. And you had one called Viking Horde that also had Google Play stores. They love those names. And the interesting thing is that there's always solutions being developed to countermeasure that malware. And Malware Bytes is it's a pretty big player in this industry. You also have your IDS's Snort. You do also have a lot of prevention for specific hardware. And the thing is, just to tell you, this is not going to be a talk about how to be a black hatter. This is going to be a talk about a specific technique and a specific category of techniques. And as I mentioned, they go by many, many, many names. You can even go and find some other new names if you want. I did think I saw some in some forums, they call it as instruction flowering, which I do think that it's a specific technique in obfuscation. But the most interesting thing about all of those things is that they usually are pretty obscure, as in you wouldn't find them in a regular technical book. Actually, I do think that there is only one or two actual textbooks written about obfuscation. There is not a lot of research going on. There is a lot of research about how to work around that field, because why would you even consider obfuscation? There's a lot of reasons why you would consider it, not just for malware authors. There's a lot of good people who are trying to hide things protect things is a better word, I would say. Stock trading companies is a big deal. So you have a proprietary algorithm, okay? And that algorithm, you do need to execute it on the cloud, or you do need to execute it on a client device. And you don't trust the cloud because you don't trust it for whatever reason. And if you don't trust it, you do want to compute that function, and you want to give it variables for it to be computed, but you don't want to actually reveal the instructions inside it. You just want to use the computer that you're working with as a more or less a slave, a worker. There are actually pretty cool papers in cryptography right now talking about methods for software verification. And for example, you have a function f2x, and I will basically give you an obfuscated, software verification doesn't go with obfuscation. It goes with different techniques. So I will give you a different method called f star to x, and I will give you x, and I will give you that f star to x, and you will compute it, and then you bring back to me the result. And using that result, I will be able to basically derive the same exact return that I would get from f to x. That's called software verification. It's still a field, and it's also still a work in progress. Microsoft did a few demos with that thing with a tool called Pinocchio. Do check it out if you want. Game companies, big deal for them, obfuscation, because they do deal with cracks a lot. Now, the game industry has been pretty lenient in the last years, but they were cracking down on this thing hard. Weapon manufacturers is also a big deal. Thales Group, the 9th biggest weapon manufacturers, does have a patent for software obfuscation. Let's talk about something a little bit more interesting. US Army. Embedded, this is a quote from US Army solicitation in 2012, and it says, embedded software is at the core of modern weapon systems. It's obviously the case. And they call it anti-tamper technology. And the most important keyword in this paragraph is add longevity, okay? That's the most important thing. In obfuscation, you don't always need to have a foolproof method to never have the software be breakable ever in your life, because I don't think that's very much possible. Because what the hell does obfuscation do? You have instructions X, Y, and Z, and you want to execute them. And what you're doing in here is basically trying to have the computer that you're executing X, Y, and Z execute that thing in that exact flow using data in, data out, without ever understanding what does X relate to in regards to Y in regards to Z. And that's just not possible, because anybody who's executing it on their machine can just, analyze it, can see it, X, Y, and Z. With obfuscation, the argument usually goes that the only limitation is the reverser's knowledge. And that's why we always add longevity. But I don't think you can, in a conceptual level, I don't think you can actually create an obfuscated technology that would be defeating any sort of analysis. There are techniques that go pretty close to that, actually, and we're going to talk about a little bit of it. And the entire idea of what we're talking about in here is to preserve the CIA triad: confidentiality, integrity, and availability of data and algorithms. Doesn't have to be for malware authors, doesn't have to be for game companies or DRM systems. It could be for practically anything that you want to protect on a client, on something that you do not control. So let's take a small example in here. And this example is, it's a small x86 snippet. Now, if I was giving this talk live, I would actually tell people to please tell me how do they execute this thing? I don't have that privilege, so I'm just going to go ahead and continue with my monologue in here. And this is the explanation for it. So what this does is basically moves, the first instruction moves 0 to EAX. That's an easy one. And then you test if EAX is 0. And if that's the case, you jump. Now, we're comparing a constant with, we're comparing a constant to a constant condition. That statement will always execute. That's what's called a positive opaque predicate. It means that it will always execute. If a compiler was doing a good job, it will never actually have these instructions in here. It will immediately jump to hello. There is no reason to have these instructions because there is no other cases. Let's go ahead and add a little bit of de-optimization to it. And let's try to understand what's the flow happening right now. So I added 3 more instructions, X, Y, and Z. Okay? So I had the first 3 instructions from 1 to 2 to 3, and the 4th one, which is the label. And I've added 3 more instructions. Now let's go ahead and read the same thing in here. So I'd move 0 to EAX, and then I would test EAX with EAX. And if so, and if that statement is true, that condition is true, I will actually jump to hello. I don't really care what happens with EBX moving to EAX. And then we have an SIDT statement instruction with EBP register. And then we have an RDTSC, which basically computes random time. It's a random timestamp. You don't need to do any of that because that flow will never occur. And the name of this method is usually dead code injection. So in this case, you're injecting code that will never actually ever be executed under any condition. And the entire idea behind it is to basically diffuse the analysis and try to have the analyst keep looking at what the hell is EBX trying to do and why is there an RDTSC. That's the entire idea of it. Basically keep buying yourself time. Now I do know that most people listening to this thing are smart, and for them, they would just completely ignore this thing after they read JZ hello. Let's try with a different thing in here. So we have example number 2. We have 3 arguments being passed to a function, and then we have A, Boolean operation, B minus C. Okay. Now, before you whip out your Python calculators, the answer to this thing is actually 0. And that's pretty easy to see. The answer to foo with inputs 1, 2, and 3 is 0. We have foo, we have the inputs. It's easy for us to calculate the output. It's not a problem. Now, let's go ahead and add a little bit more confusion to it. Now, remember, as I told you before, the instructions that are being executed in there are the X, Y, and Z instructions from the previous example. They are just there for confusion. This is the same exact deal with a little bit more oomph. So it's basically doing something very, very, very similar in here, but you have no idea about that just eyeballing it. You have to execute it. And if you execute it, the answer will still be 0. For the same input, you will get the same output. But in here, you're basically trying to confuse the static analysis. There is no way that you can analyze this thing, just eyeball it, because it is meant to be hard. It is meant to be hard for you to understand just by looking at it. Dynamic analysis does help a lot, but with dynamic analysis, most of the time you can only know the output of 1, 2, and 3. You can't repurpose this algorithm. There are ways to do that, but not always as easy. And the idea in here is that of most obfuscation techniques is to make it functionally equivalent, but a little bit harder to analyze. Now let's talk about the next part of our presentation, automating analysis. So I'll give you guys a small problem in here, a problem that I faced many, many times. And I will show you a solution to how I approach the problem. And that solution worked for me pretty well. And then afterwards, I'll go to the summary and tell you guys how I feel about other solutions that could be possible to solve the same problem. So let's talk about the first thing, the problem. So I got this. I was actually analyzing a malware, and I encountered something like this. This is Java, and I had basically a post request to an IP address, and it was basically sending a bunch of parameters in a message body and a post request body, and it looked like this. This is pretty easy. This is pretty easy for anybody to understand and reason with, because assuming man-in-the-middle attack is not an option. Assuming it's not an option, assuming that, for example, the post request is encrypted with something that you don't know, and you still have to reverse the encryption. You have to know what's the encryption algorithm, and you have to reverse it. Assuming that man-in-the-middle attack is not something that we want to talk about. It's not in the equation. And the thing that we are talking about in here is basically you have to look at the parameters in the code and understand it in the code. And I got something like this. This is pretty easy to understand. Moving forward, the thing that I actually got was something similar to this. So this is very, very similar to the previous slide, except that the values for that key value pairs in the map, in the parameters hash map, the value itself for each one of the keys was looking like this. There was a function called cryptor.get and a bunch of random numbers going on in it. Now, the first step that I would go to right now is to try to analyze what the hell is cryptor.get, because if you analyze it once and you understand it, it'll be easy for you to understand what the first, second, and third key value pairs actually look like. So I went to cryptor.get, and yep, actually it might be a little bit nicer if I make it a little bit like this. Cool. And we can still figure out what the parameters are. And cryptor.get looked very much like this. I know the picture is a little bit small, so I'm just going to go ahead and show it to you guys. So we got some interesting stuff in here. We have a modulus operator. We have a comparison to a 0 with a modulus operator of 2. We got some interesting XORs happening in here. We got some more interesting stuff going on. A lot of math. We got a switch statement with constant conditions in here. And we got some more switch statements with more modulus operators. We even have a try catch somewhere in there. So as the try catch occurs, it's going to throw a different value. You're not supposed to read this. Nobody is supposed to read this because static analysis just committed suicide. There are very few people who can actually read this and make sense of it. And if they can, it will take them a very long time to try to do the same technique and read again different techniques in the binary, different functions in the binary that look very much like this. And what I encountered was something very similar to this. Every single key value pair in that, I think it sent like 100 values from the device. And they were all relating to like the hardware name, device ID, the Android ID, things like that. And all of them were encrypted in a similar way. And they didn't just use cryptor.get, they used different functions too. So it didn't always look like this. There were others. How can you reason with such a thing? And easily enough, I immediately looked at this gigantic monster and I said, nope. Let's go for dynamic analysis. I like Frida. Frida is great for mobile dynamic analysis. And for those of you who don't know, Frida is basically an instrumentation framework. It's more or less a hooking framework. It basically puts a hook in wherever it is the instruction that you're trying to understand, and it will let you execute code before, during, and after that instruction. I don't think during too much. At least it's not easy. But before and after, it will allow you to do that. It will even allow you to replace function implementations with whatever it is that you want to execute. Which is great for dynamic analysis. You can even write Java. It's the only language that you can write agents with. It's called is basically JavaScript. And this is the simplest JavaScript script that you can find with Frida for such a case. And in here, we're basically just having something like com.afjoseph.test.cryptor, which is the class name that we're trying to work with. The function, and this is the implementation that I would like to print out to replace it with. And the implementation in here does nothing but prints out a log statement, calculates the real implementation, and prints to me the arguments and the return value. And that's actually pretty good for me because if I know the arguments and the return value for this, that's pretty much it, game over. I will be able to know what the hell is being sent. So that's pretty good, right? And I got this. And so I wouldn't take too much of your time with the presentation. I'm going to tell you exactly what's wrong with the picture in here. I was expecting 3 calls. I got 7. Actually, that's not 7. I'm blind. I got 10 in here. That's 7 times more than what I wanted. And if I had a boss breathing down my neck, and it means that I have to analyze 7 more locations in the binary. That's not good news for me as an analyst. That's not something that I would like to spend time on. So that actually just increased the amount of man hours that I have to spend on this binary, which is bad news for me. So there's a bunch of ways that you can move forward right now. You can try to say, okay, I have, for the first call that I care about, there is 100 in the first argument, there's 200 in here, and there's 300. So I do care about those. And I didn't see crypto.get 100, 200, 300 repeated anywhere else in the binary. So that's kind of a signature. You can say that, hey, if it was 100, 200, and 300, it means that this is the thing that I'm looking for. And you can write a script easily with Frida to let you take care of that. And you can do the same thing for the second and third key value pair. That's not a problem. Let's go ahead and look at what would happen in that case. Assuming that you actually try to print out the stack trace, and you have, yes, let's go back to this slide. Assuming you want to print out the stack trace, so you say that I am in a function called whatever, function called ABC, and I want to say that anything inside function ABC, I want to print it out. And then inside it, I will see the function arguments, and I will be able to figure out the key value pair. And this is the script that I would use for such a case. And this script is very similar to the previous one. It's actually utilizing the class and the method for the crypto.get. And this is the implementation that I want to replace it with. Now, to simplify it, getCallerInfo is a function I made. It's basically just printing out the call stack in Java, which is pretty easy. You basically just throw an error, throw an exception in there, and then you catch it and you try to figure it out. The getCallerInfo is a little bit verbose. It didn't fit in the slides, but that's basically what it does. It's not too hard to just search for it online. I'm printing it out so that I can basically say, okay, so if it's inside ABC function, which is supposedly this one, I can continue forward with my analysis. And then I'm calling the real implementation. And I got something like this. Basically, all of them had the stack trace more or less broken. The debug info was showing the same line. All of them. So basically, it's telling me that all of those calls are being made in the same exact location, which is not possible. But if you dig through, where does this line 1 come from? Because it's in the stack trace info. So where does it come from Android's perspective? And you see that this is actually, what you're looking at is the disassembled Smalley, which is the representation of the Dalvik bytecode. It's an easy to read representation of the disassembled bytecode, Dalvik bytecode. And you can see in here that they're all following the same line. And this is actually quite interesting because this is a common obfuscation technique. You can technically, in Android's documentation, have each stack trace parent out exactly the same info by manipulating the what's called debug info table, which is something that, sorry, debug info item, which is something in the Android documentation, and the link is right here. You can have every single stack trace print out the same thing. You can even have it print out different information. That's possible because all of that is just debug info that has no bearing on the implementation. And it turns out it's a common obfuscation technique. So there is very little ways that you can move forward with this thing right now because you, as an analyst, have no idea where those functions are executed. You do know where they are. It's in a function called ABC, but the program itself has no idea where the stack trace, with the stack trace, the info that you get, it has no idea to tell you that this is ABC or not. So this is interesting. And Java doesn't have a concept of the Dalvik virtual machine, and the ahead-of-time compiler for Android doesn't have a concept of the EIP, or like a instruction pointer. It's not something that you can access. It's something hidden. That's the entire idea of a virtual machine. They hide this implementation for you. So you can't just say, please print me the where the instruction pointer is, and I will figure it out later. So we do have a couple of ways we can actually still move forward with this and don't have to investigate 10 other locations. In reality, there were more like 100 other locations. The thing that most probably, that's the solution I chose, which is relining the APK. So relining the APK would mean that I would reline, actually, let me come back in here. I would reline all the APK debug lines in here. I will basically fix it. I will make it print out with a very low threshold. So like basically 2 instructions or maybe even 1 instruction per line. And I will fix the stack trace. I will fix the debug info item myself as an analyst. And then I would go ahead and rerun the Frida script and see how that thing goes. And ideally, what I would like to see as an analyst is something like this. I will basically just give it the function that I would like to monitor. Not even the location, just the function. In this case, I want to monitor crypto.get. And basically, I will have a tool or something annotate the execution flow. And I have a little demo in here, but I think I'm running a little bit out of time. So I will show you the result of the demo right here. The actual tool is in a GitHub repo under my name, and you can go ahead and check it out. And it's called Decrypticon. I had so much fun naming this tool. Now, what I would do to run it is basically run the test suite. And that would basically create an emulator, and there's a test project, and it would run it for you. For the sake of saving some time, I'm going to just go ahead and show you the result. So I have in here, I hope everybody can see this. I have in here an app, and it's an Android app because we're working only with Android right now. And in here, if we go into main activity, you'll see something very similar to what we just talked about. You will see in here a hash map. And then you will see crypto.get with some numbers that you don't know. And you see something similar in here and something similar in here and something similar in here, yada, 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 until you're actually sending the request to some unknown location. And this is something very similar to what we just talked about. Now, let me show you that after running the tool, how this will look like. If I had a little bit more time, I would actually run the tool and show it to you right now. But if you would like, you can just clone the repo and run the script. The script should set you up with everything that you need. For the sake of simplicity, I'm just going to go ahead and show it to you right now. And if I search for Decrypticon, I will see that underneath every single call to crypto.get, I will have, after running Decrypticon, a small annotation. And that annotation will tell me the input arguments and the return value. And it would look something like this. So at line 114, which we're looking at right now, it'll tell me neverwhere. And then afterwards, after running it with 99, 66, and 99 in here, which if you remember corresponds to, might be a nice idea to open it up right here. So something like this, when converted into when being executed, it will result in 1234, 1234. And this address 2, which is for arguments 55, 22, and 32, let's check it out. 55, 22, and 32 will result in Baldur's Gate. And if anybody knows what's this reference, you're going to know that I'm a gigantic nerd. And that's basically the tool. That's the entire idea of the tool. There is a couple other functions that it does, but the entire idea of it is that it wants to tackle layered Java obfuscation. I say layered because this tool disregards any false opaque predicates. It disregards any path explosions with static analysis. The entire idea of it is that it wants to basically, it will execute everything dynamically with whatever it is that you give it. So if you give it one function signature and you give it in the, let me see if I can find the hooks. So this is the hooks file that it works with. You have to give it a function with this signature, and this is a common Dalvik virtual machine Smalley signature. So it's easy for you to understand it. If you give it this signature and you just give it like 20 functions, it will hook into those functions. And that's basically the entire idea of it. Now I'm running a little bit out of time in here, so I'm going to go ahead and fast forward. The entire idea of it, as I said, is to annotate the results. Reline is an actual word. My friend made fun of me for it because he thought that I was just making it up. It is an actual word. I was using it way before I knew that Merriam-Webster actually had a definition for it. So I'm going to skip this slide in here. Now, I want to talk about the future, and this will be the last slide that I will talk about. The future of this tool is that I would like to include a little bit more simplification techniques. De-obfuscation is another word you can use. The thing that would be really, really, really interesting if I start moving to the native layer. And for this, I actually require your help. So if you have any techniques that you encountered of obfuscation in the wild, and you think that there is a possible way that you can have a semi-automated tool to help you with the analysis, please do contact me, make an issue about it. Do talk to me on Twitter. I'll have the info in at the last slide. And it would be actually really cool to have this more like a framework for simplification techniques. Ideally for Android, possibly we can move to some other layer later. One thing really cool that I'm working on right now is to try to use symbolic execution to simplify the code base. So I will give it a function. It will symbolically try to execute it, and then basically try to just show the registers that are moved and the functions, the actual summary of the function and what occurs. And it would make analyzing functions a little bit easier. I do know that there is a few projects that look very much like what I just did, and one project that is amazing that does basically exactly what I just said. Tries to simplify functions. It's called Simplify, and it's by a gentleman called Caleb Fenton. Very, very smart project, very, very promising. It would be really cool to have a little bit more thought process into those kind of techniques. Thank you so much. Thank you so much. Do reach out to me if you have any questions. Do reach out to me if you just want to have a discussion about obfuscation frameworks. This is my bread and butter. I love this thing. And this is my website. The slides, a little bit fat slides that include a little bit more information summarizing what I just said. You're going to find it on my website. And well, thank you so much.